parameters in vacuum problem, if you want to solve them, you need to know infinitely many of those string vertices at once, unless you know some kinds of relations between them. So this is why it is such a difficult problem. But why am I talking about it now? The reason is quite simple. Recently, there has been a flurry of activities regarding hyperbolic manifolds and Mirzakhani-like recursion relations, which actually led to a lot of progress in theoretical physics, including, say, JT gravity. And also recently, in string field theory, we have begun to adopt the idea of hyperbolic structures. For example, recently, Martin and Kevin constructed hyperbolic string vertices, and they show that they prove the BB master equations, hence the consistent string field theory. And then Atakan and Nico proved that there is a recursion relation. There's a kind of like recursion relation for string vertices, which could be potentially very useful to address some of the non-productive questions. And again, this is the point that I already mentioned. So this is why I want to revisit vacuum problem. And because this is a topic not many people are actively thinking about these days, I want to give you a brief overview so that you can just look at this slide and then zoom out and then come back later. So what I'm going to try to do is to rewrite the vacuum problem as a quadratic algebraic equation with some simplifications that I'm going to make. The starting point is the equations of motion of string field theory, which contains infinitely many terms, which is a horrendous equation to solve. What Atakan and Nico did was to rewrite this guy using the recursion relation as a quadratic integral equation. But I want to emphasize that this is still a very difficult equation to solve because those terms actually contain infinite derivatives, and this is also an equation over infinitely many fields. And what I'm going to show you today is that there is a way to actually simplify this quadratic integral equation into a triangular equation, and also there is a further simplification where you can turn this whole thing into a quadratic algebraic equation in scalar sector. Okay, now let's talk about string field theory because I'm going to use it. So what is string field theory? In a simple manner, string field theory is just a machinery that turns the Walsh's CFT into an offshell action for string field. So, here is the string field theory action, and then you can vary the action to write down the equations of motion, and then you can solve it and do lots of different physics. The core idea of string field theory, as Ashok reviewed in the morning, is to divide the moduli space into the vertex region and the Feynman region. The vertex region give you the elementary string vertices that show up in the string field theory action, and then to construct one, you need to put a metric, and you need to also choose some extra offshell data. As Ashok reviewed in the morning, an important thing that you need to ensure is that the moduli space will be covered exactly once if you include the vertex region and the Feynman region, and that will give you the solution to the BV master equation, giving you the consistent string field. So then what is string field theory good for? Ashok gave us lots of different examples that are good ones. Basically, the upshot is that because string field theory gives you an offshell prescription, any problem that is difficult to solve with the pure on-shell prescription can be somehow dealt with string field theory, or you can try to use string field theory for those. And one of those problems is the problem of vacuum solution, because the crucial thing is that even if you don't know some of the Walsh's CFT description of some backgrounds that you want to study, you can use string field theory to find the background solution and then study physics therein. So this is the idea that I'm going to use. But as I mentioned, because string field theory contains infinitely many fields, unless you have a good idea about what you're doing, it's going to be very difficult to do anything with string field theory. So we're here. We have just written down the equations of motion, including infinitely many terms. Now let's talk about hyperbolic string vertices. So what do I want to do? I want to simply do the following thing. I have some string vertices or Riemann surfaces with punctures. I want to put hyperbolic metric. And also, if I want to define string vertex, not only do I need to put a metric on it, I also need to decide which part of the moduli space of the Riemann sphere with punctures are included in the vertex region and which are included in the Feynman region. So I think it's usually much better to look at some diagrams. So let's think about 4-puncture sphere. And then this diagram, this Riemann surface has one complex structure, one complex dimension moduli space. And at a generic point in the moduli space, the 4-puncture Riemann sphere looks like some pet diagram. And what you can do is to study systole, which is a minimal length of some simple geodesics. And then you can see that the geodesic is kind of large. On the other hand, what you can do is to take a limit in the moduli space so that the Riemann surface will become longer and longer, and it starts looking like 2 cubic Riemann surfaces or pair of pens joined by a long neck or a propagator. And when that happens, the geodesic that I'm drawing here is becoming very, very small. So then you can get the idea that maybe you can use the systole to decide which is the vertex region, which is the Feynman region. And that was essentially the idea of Kevin and Parton. So more precisely, here is the prescription. Let's choose a cutoff length for the geodesic where it is bounded from above. And what I'm going to declare is that as long as the systole is greater than or equal to some cutoff length, that region of moduli space is included in the vertex region, and the rest is in the Feynman region. And Barton and Kevin proved that this solves the BV master equation, so you can use it to quantize your theory. And I want to eventually use this for the Mirzakhani-like recursion relation. So let's briefly recap how the Mirzakhani recursion relation was proven for the volume of moduli spaces. So there is this amazing identity called McShane identity. The idea is basically that you look at one puncture and then send a ray orthogonal to the boundary of the puncture and then see where the ray goes. And then some of the rays will go to other punctures, or some of the rays will intersect itself. And then you can fatten the graph. And the rays that go to the other puncture will look like as if you are joining a pair of pens with one neck to some other Riemann surface. And then the other guy will look like as if you're joining 2 necks into some other Riemann surface. So basically that's the identity here. R is representing joining 1 neck. D is representing joining 2 necks. And then what you can do is to first write down the moduli integral using Weil-Petersen measure, and then just insert this identity. And because of the fact that this guy, those terms can be represented or understood as different ways of cutting the Riemann surfaces, you can rewrite the whole thing as a recursion relation for the volume of the moduli spaces. Okay? So the important thing here is, though, this is volume of the bare moduli space, and if you want to use it for string field theory, there are extra ingredients that you need to put in. And the extra ingredients will be CFT data and the fact that for the construction of string vertices, you need to only you should integrate over only the vertex region. So there was and the breakthrough made by Atakan and Nico is that what you can do is to first define this indicator function. Basically, this indicator function is a step function that is vanishing when you're in a Feynman region and is 1 when you're in the vertex region. And then you can do some regularization to rewrite the indicator function like this, but the detail is really not important. Once you have the indicator function, you can add that or insert that into the Mirzakhani-like recursion relation with some data of the CFT, and then that will turn the recursion relation into the recursion relation for string vertices, where here we are having 1 neck joining, and here we have 2 neck joining, and the L1 and L2 are just the total lengths of the necks. And now, because we're including one more ingredient, the indicator function, now Mirzakhani kernels R and D are twisted, and therefore the twisted Mirzakhani kernels. So this is good. Now we have a recursion relation for string vertices, so you don't need to really construct higher string vertices explicitly. And if you pictorially represent the recursion relation, it looks like this. So can we do more? Can we use it to solve some vacuum equation? That's the extra step that Atakan and Nico took. So the idea is as follows. Say that you want to write down the generating function for string vertices, basically like the pattern. Then what you can do is to first write down the recursion relation in terms of constraint. Basically what this guy is doing is to take the derivative in the string field. So this generates the string vertex. This guy is cubic. This guy is basically a twisted arc tunnel joining one neck. This is joining two necks, and this is some torus one tab. So basically, this is rewriting the Mirzakhani-like recursion relation for string vertices, and because of that, we know that the generating function should satisfy this constraint equation. And after using some field redefinition and taking some, well, you don't have to take the classical limit, but if you care about the tree-level vacuum equation, you can take the classical limit. And this is the final form. Basically, this is QB of the usual string field, and then the solution of this quadratic interval equation is again the solution to the full vacuum equations in motion. One thing I want to really stress is that all those terms that are appearing here only depend on the cubic data. You don't have to construct higher vertices, so it is a much simpler situation. But of course, this is still a very complicated quadratic integral equation depending on infinitely many fields, and string vertices, even a cubic, contains infinitely many derivatives, so it is a very difficult equation to solve. So here we are, we have come this far. So let's try to simplify this equation. Capital L is the cutoff length for the string vertex, because when we wanted to define which region belongs to Feynman region and vertex region, we had to put a cutoff length, right? That's the cutoff length. Okay, any other question? Then we move on. So here's one thing, as I've been saying over and over again, this depends on the twisted arc tunnel and cubic vertex, and this depends on twisted leaf tunnel and cubic vertex. So essentially, this is adding one additional neck or sim in your diagram, and this adds two additional sims into your diagram. So what you can do to simplify the situation is to rewrite the string field in terms of the sim. So basically, you can grade the string field in terms of sims, and then of course genus 0 n+3 vertex will also be graded by n sim. And what you can easily show is that if you rewrite this string field in terms of the sim grading, then you can write down triangular equation that you can solve order by order iteratively. So let's start. So at the 0th order, because B contains one sim grading and C contains two sim grading, at the 0th order you should discard them. And this is a simple equation, basically a quadratic equation, but it is still a complicated one because cubic vertex contains infinite derivatives. Now, assuming that you have found the solution to this equation, you can write down the first order sim grading, first order equation, and then as you can see, this thing only depends on the right hand side of the equation only depends on, again, cubic, and you don't have to really solve integral equation because this only depends on the solution of the 0th order equation. And this structure persists at high orders, and what happens is that once you have the solution of to the 0th order equation, then all the higher order equations can be just iteratively solved. But again, this is still a difficult equation to solve because there are infinitely which is a very ugly PDE. So if you want to make a further simplification, there is one thing that you can try. If you know about Schnabel's open string packing solution, what he did was to just look at the so-called universal circle. basically it only contains scalars in a way. So you can also try to look for the homogeneous scalar sectors in the closed string field theory. And the nice thing is that those scalars are just vanishing if you act them with the derivative. Of course, there is no guarantee that there is a non-trivial tachyon solution in this sector, but also this is one of the simplest things to think about. So it's going to be unwise to not look for any non-trivial solution in this sector. So basically, let me get back to the 0th grade equation. This is the equation. But really, at the end of the day, if you look at the scalar sector, it is just an quadratic algebraic equation of scalars. And then once you have the solution to this, then you can iteratively solve higher order equations. And it doesn't really require much work, if you want to do some level truncation. And I would say that this is a much more tractable situation than the original problem of the tachyon solution, tachyon vacuum problem. Okay, so this is it. And there are many open questions, of course. I haven't checked whether or not there is an exact solution to the 0th order equations in motion. So it's going to be important to check that. And I think it's one thing that is potentially quite interesting is whether or not to ask whether or not there is a generalization of this recursion relation to superstring field theory. For example, can you construct superstring field theory based on the super-Riemann surfaces? I think there should be one because we have a well-defined PCO-based superstring field theory, and that we understand how to do things in super-Riemann surface formalisms. So we just need to translate PCO language into the off-shell data into the super-Riemann surfaces. And then once we have that, you can ask, is there a super hyperbolic vertex? And then is there any recursion relation for super hyperbolic vertices with a real structure? And I think a paper by Stanford Witten showed that there is one, but with the real structure. So I think it's going to be quite interesting to generalize this to more physical situations. And then the final question is, can we solve a recursion relation? And I want to be upfront about something, which is that I did this work with the help of AI. One thing, in retrospect, the idea of this project is really simple. You just need to find a good organization principle. But because I was very ignorant about this subject, I couldn't really easily spot this structure. And then I had to ask AI numerously, because I think whenever I'm trying to study some new subjects, I always get confused and I need to ask a bunch of stupid questions until I actually understand the subject. And also, Zembin also mentioned that in a way, AI can act as a very advanced Mathematica, which is certainly true, because to gain some insight, what I typically do is to do a bunch of different calculations and see if there is any pattern. So certainly it is helpful in that regard. But I guess one can still say that if you want to do research, you still need to provide research direction to AI, and it is somehow lacking the taste. So I think it's an interesting question to ask, can AI do more? Can it do some autonomous research? And I want to talk about some stupid opinions of mine regarding that. In my opinion, actually, the lack of research taste of AI seems to be strongly correlated with the fact that it doesn't really have a strong character, it doesn't have a strong bias, it doesn't have an obsession. By that, what I mean is that, if you look at every good researcher, they all have very strong feelings about which direction is promising and which direction is not, even if those feelings can be misguided and wrong. But if you push AI to have certain strong opinions, they kind of refuse to do so, refuse to say so. And the other important thing that I think is true is that, as long as one's opinion is not heavily influenced, not just reciting other person's opinion on the web, having some strong opinions and obsessions and ignorance is sometimes a good way to generate new ideas and have some diversity of thoughts, right? But then somehow AI is only able to recite that is what is already on the web in a way, because that is how AI is trained. But I really believe that this is, in a way, due to the fact that the AIs are trained to be, you know, commercially valuable and helpful for the customers. So I think there are probably a different way to train AI in a way that it is helpful for research and so that they can also do some autonomous research, although I can be very wrong. So I rather that this is a fixable problem, although I don't know if that's true. Okay, let me now conclude. I think closed string tachyon vacuum problem is a very interesting one because it combines all kinds of different ideas from different fields. And I think hyperbolic string vertices are particularly interesting kinds of string vertices that might actually help us understand non-productive physics. And if you simplify your situation into the scalar sector, actually you can just rewrite the problem as a quadratic algebraic equation, which is very good. And this is not something that I talked about, but there are also different ways to organize your expansion. But if you're interested, we can talk later after the talk. Thank you. Yes.
Yes, please.
Thank you for the nice talk. So with the we know thanks to work of Ashok and others that for the open string tachyon, the vacuum is that there's no debrane there. The debrane goes away. What are some possible closed string vacuum tachyon vacuums? I mean, answers. What do you think the answer to this question might look like, or some possible ways it could look?
My honest answer is I don't know. I know that some people have speculations about the endpoint, but I honestly don't know. I think the right thing to do is to find a solution and then say compute the spectrum and see what happens. But at this moment, I don't really have a good answer.
Okay, I mean, an obvious extrapolation from the open string case is that the space-time disappears and there's no strings there anymore. Is that a plausible answer?
It could be, but I don't know. Yeah, I think an honest thing to say is that, you know, we need to find a solution and then quantize the spectrum and see what you get out of it.
Okay, any other?
So since you have a quadratic equation of motion, is it conceivable that there's a cubic action?
I don't think, well, I think Barton proved that there is no cubic action because if you try to cover the moduli space of four punctured Riemann sphere, you cannot cover the moduli space entirely using the cubic vertices.
I thought you weren't quite in his framework because I was a few minutes late for your talk, but I thought you weren't quite in the framework Barton assumed because of the way Mirzakhani's thing entered.
Oh yeah, but this recursion relation doesn't really imply that you can cover the entire moduli space just with the cubic. It's just that there is a recursion relation between string vertices.
If it recovers the standard perturbation theory, it's hard to believe it is not somehow generating a covering of moduli space.
Sorry, could you say that again?
Well, if you're recovering the standard perturbation theory, you must somehow be generating a cover of moduli space. But regardless, you could look more directly for an action from which your equation comes. It's not clear to me why you think Barton's result would imply that it can't work.
Yeah, maybe, but I think it would be difficult to imagine that there would be a cubic action for closed string field theory. But maybe, yeah.
Hi, thanks for the nice talk. Can you say some words about what class of non-perturbative problems you think string field theory can help us understand?
To be quite frank, say the instanton physics, the instanton calculus is a good example. But besides that, it is not clear how much you can do with string field theory to study genuinely non-perturbative physics. I think the formulation itself is still very perturbative. So yeah, I think we need to try to develop the theory further to see how much we can carry string field theory with.
Would you expect this to go beyond the BV-BRST formalism? Like, what sort of changes could there be?
You mean if we want to have a non-perturbative formalism?
Yes. Not fully non-perturbative, but at least some aspects that are not currently accessible.
Well, certainly BV formalism requires you to think about infinitesimal transformations. So if there is a better way to organize a theory, that would be certainly good. And in fact, I think the gist of the problem is that we formulate the theory in terms of algebra, which is kind of forcing us to think about local physics around the point that we're expanding around, which is infinity algebra. So I think the right thing to think about is that it's kind of like Lie algebra versus Lie group type of situation, right? We start from Lie algebra. Is there a group structure or global structure? And apparently there is. I forgot the exact name, but it is some groupoid, infinite groupoid. Basically, you can construct the algebra around some point in the infinite groupoid. So an interesting thing to think about is that can we formulate some string field theory or more global version of theory using that kind of an idea? But it's pure speculation. I don't have a good answer for that.
Thank you.
Okay, so let us thank the speaker again. Okay, so our next speaker is Fyodor Popov from Simon Center, and he will talk about very strange things, how to get order at high temperature. So it is something revolutionary, and I hope you will appreciate it. Please.
Thanks to organizers for this wonderful conference. I really like a lot of talks and posters, so thank you for organizing that. And second of all, I would like to thank organizers for the opportunity to present my recent research work. My talk will be based on the following 3 papers that we've written in collaboration with these co-authors, Dr. Komargovsky and Lucas and Tinson and Passage, who are professors at Simon Center, University of Colorado Boulder and University of Durham, and Yuki Han and Xiao Yang Huan, who are postdocs at University of Colorado Boulder and Perimeter. And in this paper, we try to answer the questions that people try to address since ancient times. Namely, whether it's possible to have spontaneous symmetry breaking that is persistent up to infinite temperature. And we found that the answer is yes, and the mechanism or principle that allows to have decided to hold an entropic order. And hence, this is the title of my talk. And the main goal of my talk is to explain to you what the entropic order is, how it works, and show you various models, 15 lattice models, where you can see how this entropic order works. So let me start with some motivations. The first motivation is purely academic. Why not? It sounds like an interesting question. Second motivation is very practical, that there exists a lot of materials that exhibit interesting properties. For instance, here I took as an example some salt, and you can see that on the y-axis is temperature, and the x-axis there is some other parameter, magnetic field. And we see that at low temperatures there exists interesting properties that it becomes a ferromagnet. So it's very important because of this we can glue magnets and attach our souvenirs to the refrigerator. But this interesting property could also include some other interesting things like superconductivity or superfluidity. It would be nice to have these properties at room temperature, because of this way we can maybe reduce electric bill, at least in the United States. But after that, we will see what are these properties connected, what we will see is that they're connected to spontaneous symmetry breaking. And thus, if we want to extend these properties to room temperature or even to infinite temperature, we need to answer on the questions that I asked in the introduction. Whether it's possible to have a spontaneous symmetry breaking persistent up to infinite temperature. So it's practical motivation, and the other motivation is highly theoretical and it's coming from the adhesivity correspondence. In our community, we believe that thermal keep states are dual to the large black holes in an antidecitor. And spontaneous symmetry breaking usually means that we have some order parameter that is charged under symmetry that gets non-trivial condensate. And if we translate what does this condensate means in terms of black holes, it's equivalent to the question whether this black hole has a hair. And hence, if we answer a question about whether it's possible to have spontaneous symmetry breaking persistent up to infinite temperature, or prove that it's impossible, we are trying to address questions about no-hair theorem in antidecitor. So based on these motivations, let us try to address this question. For that, let me briefly remind you how we usually think about spontaneous symmetry breaking. So spontaneous symmetry breaking was discovered by Pierre Curie in 1890s, where he took a sample of a metal and studied what happened when you significantly pulled it down. And he observed that at some point, around 77 Kelvin, it became a magnet. So all spins of electrons become directed in one direction. At that time, it was a very surprising discovery, because people believed that symmetric law of physics should lead to symmetric outcomes. So Pierre Curie didn't believe in his own results. Later on, Pierre Weiss came up with an explanation for this phenomenon. He developed a field and showed that the effective potential as a function of the order parameter magnetization has the following Mexican cut potential, and hence if we want a stable state with minimal energy, we need to put our system around one of these vacuum states. After that, Landau, in his paper about classification of phases, gave the following explanation or conjecture about the order of spontaneous symmetry breaking. He said the following: assume that we study some one-point thermal expectation of some one-point function of some operator O. Then, usually following usual law of thermodynamics, this expectation value is equal to the following ratio. This integral over all possible configurations with this given probability, e to the minus e over t. After that, he pointed out that as soon t goes to 0, this factor becomes more important, and hence the system will try to live around one of the vacuum states, for instance here. And after that, if we do local updates of the system using Monte Carlo Markov chain procedure, we will see the system always exists around this point. But as soon as we increase temperature, entropy becomes more important, and the system will try to visit both of the universes at the same time. And from that, he concluded that at small temperature we must have spontaneous symmetry breaking, and at high temperature we must have restoration of the symmetry. I will call this mechanism energetic order, just Antonin to the entropic order. And let me show to you that even though a lot of examples that we know so far follow this idea, there exist two interesting counterexamples from real nature. So the first counterexample is quite simple. It's so-called Rochelle salt. It's not something supernatural. You can go to Amazon or Taobao and just order it tonight. It has the interesting property that, as in the experiments of Pierre Curie, this material exhibits spontaneous magnetization, but not around 0 Kelvin, but around 0 Celsius. So at low temperatures, it is the disordered state, it respects symmetry. At high temperatures, in the disordered state, but in the middle, around 0 Celsius, it has no zero magnetization. So it suggests immediately that previous arguments missing something, it's incomplete. To understand what is happening, I will address the other counterexample. For that, I need to go to the basement of some old research institute in Russia, Institute of Cold Temperatures in Moscow, and I will find there an old clear state that contains a small chamber filled with liquid helium-3. It's put under very high pressure, 10 to the 5 atmospheres. And if I study the phase diagram of the system, we will see that at high temperature it is liquid, at low temperatures it's solid, so nothing supernatural. But if I study the latent heat of this phase transition between solid and liquid state, I will find out that it's actually negative. Meaning that if I take this gray state and start to work, as soon as it reaches this critical temperature and liquid helium-3 solidifies, it will absorb heat from surrounding sample and will allow us to reach much more low temperatures. So it's very interesting phenomenon. And Pemerchuk actually explained why the system has a negative latent heat. He just pointed out that using thermodynamic equalities negative latent heat means that the entropy of the solid state is higher than the entropy of the liquid state. And he pointed out where this excess of entropy is coming. He just said that we have a solid state, we have some additional vibrational degrees of freedom that contribute to the entropy. He made some estimations and showed that actually nothing can set with observed negative latent heat. And from that, people decided to call that commutative effect. And from that, we see immediately that our assumptions that simultaneous symmetry breaking must be connected to energy is incorrect. There is some additional mechanism. And to understand what is missing, we need to make the original Landau conjecture or theorem much more rigorous. And luckily, it was done by Robert Abrushin, a Russian mathematician, who managed to prove the following theorem: that for a wide range of lattice models, there exists some critical temperature T star, such that for any temperature larger than Tc, the Gibbs state, kernel Gibbs state exists and unique. So let me formulate this theorem. So it requires only two things. First of all, it requires that interaction of this lattice system is local. And second of all, it requires that the Hilbert space of this lattice model is factorizable. So it means that if I cut out small subspace, small piece of my lattice model, then the Hilbert space is equal to the under product of the outside Hilbert space and inside Hilbert space. And the dimension of the inside Hilbert space is finite dimensional. Then he managed to prove in two different ways that there exists critical temperature and unique state at infinite temperature must be unique. So let me show how he proved it. For that, he introduced so-called operator Ti. It's operator that thermalizes given spin I, for instance. It just takes your density matrix and replaces some other density matrix such that at given spin, the usual Gibbs Boltzmann probability distribution. After that, he took specific pattern, so he took the product of these thermalization operators and said that Gibbs distribution should be a fixed point of this equation. So it's product of all of these thermalization operators, and your Gibbs state is actually a fixed point of this equation. After that, he managed to show that for significantly high temperatures, this thermalization operator is actually a contracting operator. And using theorem from functional analysis, we must immediately conclude that first of all, this Gibbs state must exist, and second of all, it must be unique. So it's a very nice abstract theorem, but if you want, there is much more physical intuition what's happening. He just managed to show that this following expansion of this Gibbs state actually exists and has a finite radius of convergence. After that, if you compute the one-point function of any odd operator, you can show that in any order that this must be equal to 0. So it seems that we have a no-go theorem, and I should end my talk a little bit earlier. But as any other no-go theorem, it doesn't constrain us, it liberates us. We just need to find what assumption seems to be very strong. And here what assumption is very strong is that we assume that locally we have a finite dimensional Hilbert space. And this assumption is very strong because if you study the most simplest toy model of QFT, the one that we give to students, is just a system of coupled oscillators. And here the Hilbert space is immediately locally infinite dimensional. So instead of now considering lattice model with finite dimensional Hilbert space, let us consider models that locally has infinite dimensional Hilbert space. So let me just immediately show you this model. So for that we will take our beloved Isaac model. So it's this 5x5 lattice. At each side we have spin variable string I that equals plus minus 1. But on top we add the following degrees of freedom. At each edge we add a bosonic degrees of freedom Nij that takes value in all positive integer numbers, 0, 1, 2, and so on. And the only purpose of life of this Nij is to control the interaction strength between sigma I and sigma j. So the Hamiltonian will have the following form, and plus 2 is added here is for convenience to make the Hamiltonian positive definite. At first glance, this model seems to be quite complicated, but actually one can notice that this bosonic degrees of freedom could be easily integrated out. And after that, we will get the resulted effective Hamiltonian for the spin subsystem actually is the same Ising model, but whose temperature is some complicated function of these parameters A and B that was in the original Hamiltonian, and temperature T that is set by my thermostat. And after that, I will observe that this function T effective has the following property that is bounded from above by this inequality. And after that, by tweaking parameters A and B, I can always make this upper temperature as small as possible. And for instance, I make it as smaller than the critical temperature phase transition of my original 2D or 3D Ising model. And hence, I will see that my spin-size system will always be in the ordered state. And for instance, if you do now Monte Carlo simulation for this choice of A and B, you will indeed see that sigma j will always be in the ordered state for any arbitrarily high temperature. So at first glance, it seems to be a very nice model. I'll show immediately that we can construct these models with persistent symmetry breaking, but this model seems to be quite artificial. To make it less artificial, let's just consider some other model. So that we take antiferromagnetic Ising model, but rewrite it in terms of variables ni, states value 0, 1, and the interaction between adjacent sites by the following parallel interaction, where a is some number bigger than 1. After that, I will note that this phase diagram for the antiferromagnetic Ising model follows usual properties. At low temperature, it exists in the ordered state. At high state, it exists in so-called gaseous state. I will refer to it as checkerboard. At high temperature, gaseous state. And now let us try to play the same kind of game that we played in the previous slide. So we say that NA now is not 0, 1, but goes from 0 to infinity. So it values in all integer numbers. And after that, to make Hamiltonian sensible, I will replace the sign of this minus by plus. So this is a model that we will study. We decided to call this model arithmetic Ising model, or for short AI model. Okay. So if you, now this model is very complicated. So we need to go to the Monte Carlo simulation to see what is happening here. And after that, we will see that at high temperature, the order of phases gets swapped. So at high temperature, it exists in the ordered checkerboard state, but at low temperatures, it exists in gaseous state. But now this checkerboard state is a little bit different than the original checkerboard state from the antiferromagnetic Ising model. Now each yellow dot here is not 0 or 1, it's 0 or t. So more or less the state looks like a downtown of Shanghai, while this gaseous state mostly looks like a it's very dense, but only one floor. Okay. So let's understand why checkerboard phase means it's a large temperature. For that, let me just estimate the contribution to the partition function coming from this checkerboard state. So in this case, I note that the only relevant interaction is the chemical potential here. And hence, as I told you before, the height of this yellow dot is of the order t. And since only half of the vertices are occupied or size occupied, the contribution to the partition function has the following form, like t to the power of v over 2. Now, if I consider what is the contribution to the gaseous phase, I will see that now the interaction becomes important, and I have a maximal gap cut on this number of on the height of this sides. It will be n t to the power 1 t to the power 1 over 2a. And after that, I will see the contribution to the partition function has the form t to the power v over 2a. And if a is bigger than 1, I will immediately see that checkerboard phase means it's a high temperature. Now we point it out, and from that we immediately see that that checkerboard phase means it's a high temperature. So let me try to understand what's happening here. It's how connects it to the Pomerantchuk effect. For that, we'll go back to this thing. So for that, I will note that in this case, when sigma j are in the ordered state, the effective chemical potential for energy is less than the effective chemical potential when z is ordered, and hence the entropy of the ordered state I expect higher than the entropy of the disordered state. So it's the same as in the case of Pomerantchuk effect, where the entropy of the ordered state is higher than the entropy of the disordered state. And I can just using this exact solution show that explicitly. And here we exactly have the same. That thanks to this ordered state, we turn off this strong interaction that allow us to fluctuate much more widely at each of the locations. So we see that in both of these situations, again, the same type of principle occurs. At high temperature, we have ordered state because of the entropy of the ordered state is higher than the entropy of the disordered state. Okay. now let me say that actually we can study the model where A is equal to 1, and now this become a very simple model. Here also we can add on top of that a fucking term between adjacent sides, like this one, or also add some species here. And after that, one can check that even though the previous argument does not work, still, if you do much more careful high temperature expansion or Monte Carlo simulations, we will see still the same type of behavior. Now, so now not for all range of parameters of U and mu we have solid state at high temperature, but only for once U is bigger than mu over 2. Then at high temperatures we will have a solid state here. Okay, and since this model is so simple, we hope that at some point in the future we will be able to find maybe some materials that has the same type of interaction, or maybe we'll be able to simulate this model using, for instance, photonic computer, something like that. Okay, so now let me go to the QFT systems. Let me show that this persistent symmetry breaking could also occur in QFT. For that, let me point out that there is no issue with the Bruch's theorem, because of once we take a continuum limit, this critical temperature of the Bruch's theorem can also go faster than any other irrelevant scale in my original model. So the Bruch's theorem doesn't have any control over this quantity series. And hence we might expect that we can easily find such model, QFT models that will exhibit this interesting property. But for a while, people managed to construct it with only the fractional number of dimensions. But here we will present some models that exist in 3 dimensions. For that, I will consider another beloved model of theoretical physics, namely large n vector model, with fields and fields phi I, that coupled with the coupled subdimension field sigma. And on top of that, I will add a free scalar field psi. So together, this model has ON cross C2 symmetry, and I want to somehow manage this two systems interact in some interesting way. And the only way that interactions preserves ON cross C2 symmetry is this type of interaction, sigma psi squared. This interaction is slightly relevant in the large n limit because of psi has dimension 1/2 in 3 dimensions and sigma has dimension less than 2 in 3 dimensions 2 minus 1 over n. So I can take n to be very large and it will be slightly relevant. And after that, I need to worry about this type of interaction, psi to the 6. And there is also exist interactions like psi squared phi I to the 4th, but I always can remove them by redefining my sigma field. So there is only these 2 parameters, tau and g. And after that, I can write down beta functions for these parameters in the leading 1 over n expansion. And after that, I will see that there is exists 3 interesting perturbative exponents. The first one, where t is equal to 1 and g is equal to 0. So it's my ON model just flew to the ON plus 1 model. T is equal to 0 and g is equal to 0. It's just the original model that was very boring. And there exists solution where t is equal to -1 and g is equal to this huge number. And I should be very happy because of this number is positive, meaning that this theory with t is equal to -1 is unitary. So now we have this model that exists in 3 dimensions, unitary. So maybe at some point in the future we will be able to find some material as a theory describing some phase transition. But now if I study this model at finite temperatures, the CFT, I will find out that this solution with t is equal to -1 actually breaks it to symmetry at finite temperature. That this field psi will get condensed. Now, let me try to understand how it's connected to the previous lattice models and combinatorial effects that I explained to you before. For that, I will just compute the entropy of my system as a function of temperature for disordered and the ordered state. And I will see that for ordered state, when psi is equal to 0, sigma is equal to logarithm of the golden ratio, so sigma is positive. When psi is not equal to 0, sigma is equal to 0. And because if sigma plays the role of effective mass for these ON fields, I must conclude the entropy of the and scalar fields is actually higher than the and the ordered state is higher than the entropy of the disordered state. If I do indeed computations using large n solution, I will immediately see that it's indeed true. Hence, if I fix some energy and draw randomly some state, most likely I will draw a state that has non-zero psi. Okay, so it brings me to the end of my presentation. I hope I persuaded you that we can have potential tree breakings that persistent up to infinite temperature. It would happen because of usually we associate order with energy, but now we can associate order with entropy here. And what is happening here is that again we have a genuine potential tree breakings that we have two different superselection sectors and algebra of local operators get reduced. But what is happening here is that now we cannot tunnel between these two universes, not because of our energetic barrier is high, but because of even though energetic barrier is low, but the road to go from one vacuum state to the other vacuum state is almost infinite. So in the case of arithmetic Ising model, the checkerboard state, to go from one vacuum state to the other vacuum state, we need to demolish all of the skyscrapers, move one step and build another skyscraper. And will take a lot of amount of time. And so at high temperature, it seems to be could be done almost for free. And at the end, it would be very interesting to see experimental realization of such models. Thank you for your attention.
So any questions?
Hi, thanks for the nice talk. Can entropic order be characterized in the framework of operator algebraic quantum lattice systems like GNS algebras in that context?
But could you repeat this?
Yes, but can entropic order be characterized in the language of operator
Yes.
quantum lattice systems
Yes, I
of
think
GNS algebras?
Yeah, I think so. The algebra of local operators will be reduced.
So in that case, how do these distinct vacua look like? How do I distinguish the states?
For instance, so it will look like that you have that in this case you have like these two states, for instance, in the arithmetic Ising model that looks like actually board, right? But so you have that one state. Just imagine that you move the state by one lattice step. That will be the other step. So you will mostly hang out around one of these vacuum states.
Okay, thank you.
More questions?
So you probably know there's when you have a global symmetry, there is a refinement of the Carty formula depending on the charge sector. Usually that relies on the democracy among charge sector is a kind of usual consequence if the finite temperature state is isometric. So in your case, when you have entropic order, say in the CFT, at finite temperature, what is the consequence at the level of the symmetries of the Carty density states?
It's a question here. Right now, what is best way?
So more questions? Okay, then let's thank the speaker.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始， 请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
All right, so it is my pleasure to introduce Professor In-Cheng He from Preliminary Institute, who will tell us about his fuzzy sphere journey in the conformal world. Please welcome.
So first of all, I would like to thank the organizers for putting together this wonderful conference, and also thanks for the invitation. So as a condensed matter physicist, I really who spent almost 10 years in Shanghai since college, I really find it quite an experience for me to speak in the Sijins, Shanghai. So I don't think I need to motivate you guys that why safety is interesting. And this fuzzy sphere regularization is a new method that my collaborators and myself developed to study 3D safeties. So the goal or the motivation is to study 3D safeties on cylinder. So we all know that once you put safety on S2 times R, there are a lot of nice properties of safety you can make use of, right? For example, the state operator correspondence. And by regularization, what we mean is that we want to study safety or QFT with a finite degree of freedom, such that we can put it in the computer, right? That's also this lattice regularizations is about, right? And by fuzzy, what we mean is that we are using non-commutativity rather than the lattice discreteness to do the regularization. And the reason that we want to do that is because we all know that the sphere has a curvature such that a regular lattice won't fit, right? That's why we ask for the help of the so-called fuzziness. So I think many of you know that in the past, there are a lot of interesting progress studying non-commutative field theory on fuzzy sphere. And there you end up with an interesting non-local QFT. Here we are actually, our approach is very different. And in the end, we get the usual local quantum field theories like Ising CFTs. And our approach or our perspective is to think about the so-called lowest standard level on sphere, which condensed matter friends has been studied for many years for the quantum Hall physics. Okay, so the basic idea is actually very familiar. So what we are going to do is to study quantum mechanical model realizations of 2+1D CFT, right? That is, people have done this for many years for those lattice models. Here, I'm just giving you an example that the famous transversal Ising models, which, for example, can be defined on a square lattice, and on the lattice side, you get a quantum spin 1/2, and then you design some proper Hamiltonian such that by tuning a parameter, here is like the transverse field, you can realize different phases like Ising ordered phase and also disordered phase, and in between, you get a quantum phase translation, right? And this, here for the Ising, you will get famous 2+1D Ising CFT. So the idea of our fuzzy sphere approach is really very similar, right? But instead of lattice model, what we are going to consider are the particles moving on the sphere in the presence of monopole, a magnetic monopole, right? But it is still a quantum mechanical model, and here is a typical Hamiltonian. The first term just is the minimal coupling between my particles and the vector potential, right? I have many particles. And then the second term are some, let's say, two-body interactions. And of course, you can study more complicated interactions. So then the idea is that we can design some proper Hamiltonians such that by tuning some parameters, we can realize a certain 2+1 CFT of interest, right? It's a very natural idea, and it was first pursued on torus by those people. And indeed, we condensed matter friends have done this for many years to study fractional quantum Hall, that is TQFT on Sphere since Duncan taught that. And now what we want to do is that to apply this to study CFTs. Okay, so let me spend, so the one key ingredient is this so-called lowest Landau level. So let me just remind you what it is. So as I said, what we are going to consider are the electrons moving in the presence of magnetic monopole. And then the single particle states of this will be become the Landau levels, right? That that's what we have learned in college quantum mechanics, right? So then, if the if the gap between Landau levels are much larger than any other energy scale, and meanwhile we have enough states in the lowest Landau level, so we can consider a mathematical rigorous simplification that we just project the system down to a lowest Landau level, and people know that this actually lead to the what mathematicians would call fuzzy 2 sphere, where the original sphere coordinates becomes matrices, which follows the SU2 algebra, right? So and the lowest Landau level on sphere has some nice properties. For example, it will contain 2s plus 1 states. The s is the monopole flux. And those 2s plus 1 states will form the spin s rep of SO3. And under a natural gauge, the wave functions of those Landau orbitals will be localized at different latitudes as shown here, right? So, and a typical Hamiltonian we will consider is that, again, contains this minimal coupling, which gives me Landau levels and the interactions, right? And the procedure of doing lowest Landau level is also very straightforward. For example, we have this Fermionic operator, Fermionic fields. We just replace it. It's a bit like Fourier transformation, that we replace it with the Fermion creation or annihilation operators. These are the operators create or annihilate particles on the lowest Landau level orbitals, right? Times the so-called monopole harmonics, right? So you just insert this spherical or fuzzy sphere version of Fourier transformation into the Hamiltonian, and in the end, you end up with strongly interacting lattice models or quantum mechanical models that has 2s plus 1 site, right? Those sites are nothing but the Landau orbitals shown here, right? And the continuum limit correspond to that. We have like this s goes to infinity, right? That correspond to we have infinite physical volume, and meanwhile you can say here you actually recover the continuum, the commutative sphere limit, right? The non-commuting coordinates are no longer are actually become commuting again. Okay, so this is the lowest Landau level and the fuzzy sphere. Now let me give you a concrete example that how we realize 2 plus 1D Ising CFT using this. So what we can consider is non-relativistic fermions with an isospin degree freedom. Here, you should think this isospin as an internal degree freedom. It has nothing to do with the magnetic field of monopole. It has nothing to do with the sphere rotation. So, and then with this, those fermion operators, you can write down what we will call density operators, right? By just inserting the polymetrics, right? Those density operators are really like the analog of the spin operators if you consider a lattice. But here, those density operators are defined in the continuous space rather than the discrete lattice site. Okay, so now we can use this to write down the Hamiltonian of the 2 plus 1D Ising CFT, right? As I said, the key is the interaction term, right? So now you can say that indeed this interaction term is very similar to the transversal Ising model. for on the lattice. Specifically, if you look at the second term, right, that's really like the Ising-Ising interaction, like the continuous version of the discrete nearest neighbor Ising-Ising interaction. And the second term is the transverse field, which help us to tune the phase transition. The first term is a little bit mysterious. You can think it as some analog of on-site harbor interactions. If you want to make a try to connect with lattice models, but it may have some interesting physics, which I will comment in the later part. Okay, so then the idea is that we fix, let's say, fix this interaction strength U, and then tune H. You can have a phase transition between an Ising ferromagnet and the paramagnet. It's very easy to visualize those two phases. The Ising ferromagnet will just have precisely one fermions at each lambda orbitals, and then they would either pointing down or up, which spontaneously break the Ising Z2 structure. And on the other hand, if the transverse field is strong enough, it will just polarize the spin. And that recovers Ising Z2 symmetry. And in between, by tuning H, you naturally would expect that you get a 2 + 1 Ising safety. Right, so I want to remark that for Ising CFT, those fermions won't be strictly localized at each orbitals, which means that they can actually, the charge degree further actually can move around. There will be configurations that on an orbital there is no fermions. Also, like there will be orbitals occupy 2 fermions. That's okay. So then what we can do is that we just tune the edge, we get to the critical point, and then we diagonalize the Hamiltonian to get the energy spectrum, right? The state operator, so for CFT, the state operator correspondence tells us that the energy spectrum will just be the operator spectrum of the CFT, and up to some non-universal factors, right? And then we can easily fix this non-universal factor. For example, we just require that the theory has a suggest tensor with scaling dimension 3. Then we rescale the energy gap. Then those numbers here will correspond to the scaling dimensions of Ising operators up to some fine size corrections. So we can then analyze this operator spectrum to get the to check whether it's really a CFT with conformal symmetries, and then read out the scaling dimensions. So here are just some plot that for the conformal multiplet of the low-lying primaries like sigma, epsilon, and stress tensor, right? So the symbols are our numerical data. The lines are the conformal bootstrap results, as well as from conformal symmetry, right? So you can see that for low-lying operators, the agreement actually are very excellent, but for the high operators, there are some discrepancies. Those discrepancies are something you should expect because we're actually doing the computation under a very small physical volume that is like 16 electrons. So that's like a 4x4 lattice. You want to connect with the lattice model, right? Which is very small, for which people usually won't expect to get anything useful regarding the phase transitions. Okay, and those discrepancies also can captured by the conformal perturbations. You can use that to also understand those discrepancies. Okay, so then we can read out a lot of primary operators as shown here. Like again, that's a result of 16 electrons using spins and electrons interchangeably. So then you can see that indeed the raw data that we get compares very well with conformal bootstrap, right? All of those have very small discrepancies, and the higher and for the descendants, right, it also matches very well. Okay, and I think it's already surprising that we get fairly accurate results for 16 electrons. But what's even surprised us was that if we just consider 4 particles, right, that's like 2 by 2 lattice, we still get very decent results for the CFTs. So here is the raw data for the 4 particles, and that's all the energy gaps we have. And then you can say that most of those states actually are CFT states with reasonably small discrepancy. And then among those, we have 6 primaries and 11 descendants, right? So this is really wonderful. And indeed, we can go beyond the operator spectrum. We can also compute operator correlators, compute OPE coefficients. We can also compute RG monotonic F functions. We can also apply this to study conformal defect boundaries, access a lot of information, including RG monotonic G functions, boundary center charges. Okay, so I think the fuzzy sphere approach really opens a larger world of CFT or QFT in general. It gives us a numerical handle on many previously inaccessible problems. Right? On one hand, it can help us to study many strongly interacting, strongly coupled field theories. And on the other hand, we can also use it to compute a lot of observables which are difficult for other methods like these F functions. Right? I'm not claiming that we can use fuzzy sphere to study your favorite problem, but on the other hand, at the moment, we also don't see any fundamental limitations for this method. Okay, and of course, that really requires us to explore even further, and I'm happy to say that there indeed has been growing results by applying the fuzzy sphere to many different problems. And in the rest of the talk, what I'm going to focus on is that the so-called Chern-Simons matrix theories. Okay, so here I'm just giving you an example of a very simple, probably the simplest interacting Chern-Simons matrix theories. And in condensed matter context, this theory describes a phase transition between a U1 level 2 Chern-Simons theory and the trivial phase. By trivial phase, I just mean it's a gapped phase, no spontaneous symmetry breaking, no topological order. People may also call it invertible phase. So more than 3 decades ago, our condensed matter friends already wrote down the 2 different field theories that which are expected to describe these phase transitions. One theory will have like 1 boson coupled with U1 level 2, and the other theory will be 1 fermion coupled with U1 level -3 halves, right? And but in the past 3 decades, there are very little progress try to address whether this theory, right, is really following to a CFT, or we don't even know whether it is a continuous phase transition. So, and what makes this theory even more interesting is that people in the audience actually propose that there are indeed another 2 Lagrangians which involving non-abelian gauge theories, which are probably due to those 2 abelian Chern-Simons matter theories. That is a simple example of level rank duality. And for those non-abelian gauge theories, you can the UV Lagrangian has a manifest SO3 symmetry. So that means if duality is true, then those 2 abelian theories, whose Lagrangian only have O2 symmetry, will be enhanced to SO3 symmetry in the infrared, right? And our condensed matter friends also find that if you dope this CFT in certain concrete UV setup, that is in some lattice models, you will get superconductors. Okay, and so those are really very interesting properties of this CFT, of this putative CFT, but at the moment, it was not known whether in the end there really exists such SO3 CFT, and because there was no non-perturbative method for people to study such Chern-Simons matter theory, and that's also why we were excited about fuzzy sphere. That really opens up this possibility. So eventually we have figured out that how to study this Chern-Simons matter theory, or be more precise, how to study this universality class in fuzzy sphere. So what we can consider is a system that has boson-fermion mixture. So we will have like two flavors of fermions, right? By flavor, again, I mean some internal degree of freedom, like this isospin we have for the Ising CFT, right? So now you can easily imagine that for these two flavors, we can have SU2 flavor symmetry, and this SU2 flavor symmetry will become the SO3 internal symmetry of the IR CFT. And on the other hand, we also have one flavor of bosons, and those boson and those particles carry different electric charge. So the fermions carry charge 1, the boson carry charge 2. So that means we can also convert, let's say, one boson to two fermions and vice versa, right? So this is, now we can write down a very simple Hamiltonian that describe such system, right? So we have this boson-fermion conversion, and then we have a chemical potential just controls how many particles are fermions, how many particles are bosons. So, and again, the first term is actually the similar term of that we had for the Ising CFT, like this density interactions. So, and then we have two limits. One limit is that if this mu is very large, then all the particles would be preferred to be bosons, and then that will then realize this 1/2 bosonic laughing state, which is U1 level 2 TQFT. And on the other hand, if we just make this mu to be very negative, all the particles will be fermions, and then we'll just complete fill those two lowest standard levels, which will be an invertible phase. And then in between, which we can expect there will be a phase transition, which is likely to be the same universality as those Chern-Simons matter Lagrangians introduced. So then we did numerics, and we find that indeed we get a CFT in between by tuning this chemical potential, and we get operator spectrons. And in the operator spectrum, we find that there's only one relevant operators, that is SO3 singlet, and that is a tuning operator for the phase transitions. So that also means the duality conjecture actually passes the spectral test, meaning that if you have a system with only O2 symmetry, then the SO3 can emerge in the infrared. Okay, we also get other evidences, like we get check correlators. We can also construct conformal generators to say whether we have emergent conformal algebra, right? So, and we can further generalize this scheme to the entire family of QED3 Chern-Simons with, let's say, uptree flavors of Dirac fermions coupled with uptree level of Chern-Simons term. So, okay. So I hope that I make a case that the fuzzy sphere is really a very powerful method for us to study CFTs. So let me also comment a little bit on the guiding principle that we can follow to construct how to fuzzify a CFT. So as many other methods, right, the guiding principle will be the kinematics, like symmetry and anomaly, right? For the most of the cases, we usually construct CFTs on fuzzy sphere as some IR universalities, right? You already say that for either for the Ising CFT or the Chern-Simons matter theories, we really just try to find some model that realize the same phase diagram of the CFT of interest. And also we can realize CFTs with non-trivial anomaly, right? And we can also make connections or at least get inspirations from UV renormalizable Lagrangian. So that is an example of this indeed for free fermions and interacting fermions, like this gross Uyukawa, which has emergent supersymmetry. So we are able to also fuzzify it, inspired by the UV Lagrangians. Okay, so it's like 2 more minutes. So I think all those results are really cool, and we can certainly use it to study many open problems regarding CFTs. But to me, probably the most interesting questions is that why it works so well. So that's also the question that really kept me busy for a while. So it could be that non-commutative geometry is a good way to regularize QFTs, or maybe there's some hidden structures of 3D CFTs somehow was accidentally captured by fuzzy CFT. So, for regularizing QFTs, I think our example of the free fermion CFT is probably really a good starting point. So, so alternatively, indeed, we can formulate the fuzzy sphere model as a deformation of the standard CFT. By deformation, what I really mean is that for the usual QFT, right, you have so here is for free fermions, right, you have the canonical quantizations, and then you use those fermionic fields to write down the Hamiltonian of let's say free fermion, right? And on fuzzy sphere, we also have those fundamental fermionic fields, which are like the density fields, and they follow some deformed anti-commutation relations, and then we can use that to write down the Lagrangian and Hamiltonian, and you can say that indeed the Hamiltonian is almost identical as free fermions, besides this mysterious term, which actually has connection, which doesn't have any QFT interpretations, but instead it's related to the they actually generated the area preserving diffeomorphism of the sphere. And there are also some interesting observations like related to the diffeomorphism and the CFTs, which I think I should skip. So let me also collaborate, thank my collaborators like in this fuzzy sphere journey. I really enjoyed working with them. And now, thank you.
Thank you very much for an interesting talk. Coach?
So, do you have any evidence that you are studying a Chern-Simons matter CFT, aside from the fact that it has the same anomaly?
It has the same anomaly, and it describes the same phase diagram. And for this theory, in specific, there's no other results. Like we don't know how to compute quantities like scaling dimension of Chern-Simons matter theory, so there's nothing to compare with.
Well, I guess in principle, I guess if you could look at Chern-Simons matter theories when the number of flavors is large, then you could try to make some kind of comparison.
Yeah. I hope in the future we can do that. For example, for the QED3 Chern-Simons, we can do the entire. So in theory, we know how to do the entire family. So then that includes the case flavor is large. In practice, I don't know whether it's feasible for the.
So for fermions, the lowest order level is finite dimensional due to exclusion principle, but you also include bosons in some of your constructions. How do you make the Hilbert space finite dimensional for those?
Because the number of total particles is fixed to some ratio with the number.
And then I guess you use chemical potential to control that.
Yeah.
Could you comment more on the non-equilibrium model for the fuzzy sphere? For example, we can consider some random bound model. Can we put it on the fuzzy sphere to extract some component vector?
Oh, sorry.
Sorry, I mean, could you comment more on the non-equilibrium system? So, as that case, can we, for example, consider some disordered system and then put on the fuzzy sphere to extract the conformal data?
Yeah, I don't know. Yeah, that's an issue.
Okay, thanks.
In view of time, so
Hi, thanks for a nice talk. Is there a simple embedding of this type of setups in string theory, maybe similar to the way that non-commutative gauge theory appears in string theory with magnetic fields and so on?
I don't know. Yeah, I know almost nothing about string theory, so I'm here to learn. So,
Okay, thanks.
in view of time, let's please ask more questions during break. Let's Okay, so our next speaker is Professor Mykola Dejushenko from CIMIS and Fudan University, and he will tell us about his on the EFT origins of the fuzzy sphere method.
Okay, can you hear me? All right. Thanks a lot for this opportunity to present my work. And indeed, the talk will be on the same subject. Thankfully, Yunchen already set the stage, so it will be very helpful for me. The first slide is, of course, the mandatory overview, which was already said in the previous talk, that fuzzy sphere is an excellent UV regulator, which, unlike other UV regulators that you usually work with, it both preserves rotational invariance on the sphere and gets you closed algebraic functions, whereas the other known regulators usually violate one of those. But that was, and then of course in the 20th century, people pursued that, trying to build some two-dimensional, use that for two-dimensional theories. But nowadays, since 4 years ago, we now use the to study three-dimensional CFT, and where we replace the space by fuzzy sphere, and then build some finite dimensional quantum mechanical model that in the commutative limit approximates your quantum field theory. So I would like to, and by now it has already become a really a 3D CFT laboratory. There's a huge number of papers being written on this subject, and this slide is not to be meant to be stared at for too long. It's just for you to go look at my slides later and complain if I forgot to mention your favorite paper. I will explain some ideas again, using first using the Ising model as the paradigmatic example, and then let's see what happens after that. So as Yunchen already reviewed, in the case of Ising model, we have this fermions on the lowest lambda level on the sphere. So we have a field psi, which is a combination of lowest lambda level, the density operators, and the Hamiltonian is constructed from the transverse magnetic field, the Ising interaction channel, and this density channel, which improves convergence. And the interaction is usually taken to be ultra-local with a delta function and then the Laplacian of delta function. So one of features that I want to emphasize is that the CFT in this case, like you find it in the half field sector. So there are n orbitals on the sphere, and you put two flavors of fermions. So there are, because of exclusion principle, there are two n slots. You fill up n of them, and there's a special symmetry particle, the whole symmetry, that is available at half filling, which somehow in the continuum limit becomes the space-time parity in your Ising CFT. So so when this whole thing appeared, a few things felt a little mysterious to me, but of course, just it's my own problem. But I'm pretty sure that Yunchen knows answers to all those mysteries. But as a QFT person, it's just aesthetic preference to have a QFT explanation for some of these mysteries. So The puzzle number one is that the model, the way it's written here, is very much non-relativistic. However, at the quantum critical point, somehow you end up having a relativistic CFT. So why? Why is that? And of course, we know a lot of many-body systems that at their quantum criticality, they don't have relativistic behavior. They have some non-trivial scaling where z is not equal to 1. So that's one puzzle. And another puzzle that, since this appeared, some people have been asking the question, is there some sort of quantum field theoretic explanation of this technique, or like why it works? And at the moment, the way this model is constructed is like basically you choose Landau level orbitals, you write some symmetry allowed terms, scan tune for criticality, and you rely on universality to do the heavy lifting and actually give you CFT point. And this works remarkably well. And for example, in this paper, they developed a dictionary between how you write Lagrangians and how you write interactions on the fuzzy sphere. However, as a key person, I want to know is, can we somehow systematically derive this fuzzy Hamiltonians from some local UV QFT? And can we predict when Lorentz invariance emerges and so on? And maybe even generalize away from conformal field theories. And finally, there were like a bunch of these small technical puzzles which were like somewhat surprising to me. Like, for example, this thing about the density channel, that it improves convergence, that the particle field symmetry becomes space-time parity, or, okay, this is actually a hint with CP, and so on. So I would like to sort of give some sort of unifying picture that will help answer all these questions all at once. And here's the main idea, is that there will be a quantum field theory, which I shamelessly stole the name from you know what, and called it Maury theory, which contains light mediators and massive charged matter, such that you can can do two things with this theory. You either integrate out massive charged matter and you end up with some local effective field theory with these mediators, which you can then tune to a quantum critical point and obtain some sort of Wilson-Fisher-like CFT. Or you can integrate out these light mediators, get non-local theory, which you then project in appropriate sense to the lowest Landau level, and you get the fuzzy sphere Hamiltonian. And then the idea would be that you could go this way or that way, and the two things must coincide by construction. There will be a sort of derivation of this fuzzy sphere Hamiltonian. So this slide is actually really optional. Like, there was really no reason for me to include it. I could avoid it in the whole story, but for me personally, just personal preferences, some of the hints came from Beijing Topson's quantization, which, because somehow in this business, so even though fuzzy sphere itself is a quantum system, just a quantization of sphere with its glowing form of symplectic structure, but in this business, somehow it is important to think of it by a projection to the lowest Landau level. And mathematically, that's actually precisely this Beijing Topos quantization. And there exists one particular version of it where you consider, you can formulate it physically in the following way. You consider a superparticle that moves on your manifold, symplectic manifold, in magnetic field given by symplectic form. And you project the supersymmetric ground states, and this gives you quantization. You can actually somewhat compare it to the brain quantization story of group of Witten, where instead you have superstrings that you project to supersymmetric ground states and the complexification of them. There is, presumably there's some connection. But the reason this was a motivation for me is that the Hilbert space here is actually the kernel of a Dirac operator, the spin-free Dirac operator. So I would like to think, at least in this case of the Ising case, let us think of the quantization of the Hilbert space as the space of zero modes, or Dirac operator on S2 cross time. So we have zero modes, of course. If there's flux n-1, then there are exactly n Dirac zero modes. And let's extend this side actually to the full Dirac fermion. So not just project to the lowest Landau level, but consider the full Dirac fermion. Then we can take the fuzzy Hamiltonian and simply extend and write this sort of three-dimensional theory where you have the kinetic term that couples to the flux n, so that you can project it to it's responsible for projection to the lowest Landau level. Then you have the mass term, which after projecting to the lowest Landau level, it becomes the transverse magnetic field. Then you have these four Fermi terms, which give you precisely the two channel, the Ising channel and the density channel. Now, of course, if you like to work with UV complete theories, this is not very nice because it's for Fermi interaction. So what we can do instead, use the well-known old Haber-Spravnovich trick and introduce a scalar field phi. So here I could just the kinetic term is optional. So like if you actually turn off the kinetic term, it just becomes auxiliary field. You can integrate it out, and it gives you the Ising channel. Now temporarily I dropped the density channel, but you can also introduce the density channel if you add another kind of Haber-Spravnovich field, which will be massive, and later I will not tune it to criticality, just a sort of a spoiler. But that will generate the density channel. So in the end, I end up with this theory, which now is perfectly fine, three-dimensional quantum field theory of fermions with the mass term. It's coupled to field phi, and if I integrate out phi, I go back to the purely fermionic description, and in that integration, I can actually assume that kappa is small and expand it in derivatives, in which case I will, if you only keep the first two terms, I will reproduce the ultralocal interaction that you saw previously in the quasi-Hamiltonian. As I said, the density channel can be restored quite easily by adding additional channel, the additional field rho, stable field. Now, in this theory, I can notice that the fermions in this theory, actually, you can check that the eigenvalues of the mass matrix are non-zero. They're actually given by this. So I can integrate out fermions, they're massive, and I end up with the purely local effective field theory for the field phi, which can be tuned to a critical point by adjusting parameters of the initial theory. In particular, I have to tune this R2 to get this initial critical point. And this already actually gives you sort of an explanation of Lorentz invariance, because I start with Lorentz invariant theory in the UV. I do usual manipulations. I just integrate out happy fields. I get effective theory, which so clearly you're gonna get Lorentz invariant CFT, the IR. I can also look at the symmetries here, just to answer some of the technical puzzles that I posed earlier. The Ising D2 extends now to the following symmetry, where you flip the sign of phi, and at the same time you swap the two components of the fermion. Here, actually, I have two flavors of the fermion field. So this is my Ising symmetry. The mass matrix and the Yukawa coupling, they break the SU2 flavor symmetry of the two fermions. And also, as you know, in 3 dimensions, the mass and the Yukawa, they are odd on the parity, which you might be familiar with from the discussion of parity and all that. But there's a certain combination of this flavor and parity that is preserved, which is, again, a usual story. When we have two Dirac fermions with, let's say, opposite masses, you can make it invariant under parity if you also swap the fermions. Now, when you put this theory on S2 cross R with magnetic flux, the magnetic flux is going to break for C, P, and T. But then there is a surviving operation, which is this parity, which is preserved in flat space, times C, because they both P and C, they flip the magnetic flux. So now you get Cp tilde, which is a symmetry of this theory. Now, if you now look at the lowest Landau level description, in that description, it becomes just particle hole symmetry that I mentioned earlier. If you look in the phi EFT description, there it becomes just the ordinary space-time parity, because the flavor symmetry and charge conjugation, they act trivially on the real field phi. So this, for example, explains that thing about parity and particle hole symmetry that I mentioned earlier. So here's again this picture one more time. So we have this UV quantum field theory, which has mediators and charged matter. You integrate out mediator, you get, and then do a projection, you get phi Hamiltonian. You integrate out charged matter and tune to CFT, you get your usual formulation of CFT, like phi to the 4. And there's only one meaning for this LLL projection that is consistent sort of with Wilsonian thinking, is we just have to integrate out higher Landau levels. And then as I explained, the symmetries between these two formulations match, as I illustrated on the previous slide. Now, when we do this, so the integration that I explained earlier, it was actually like this integration. It was really done in flat space. This formula for the potential that you get from integrating out fermions, it's true in flat space. Of course, when you are on the sphere in the presence of a magnetic flux, it's going to be a little bit more complicated because you have to integrate out actual Landau levels. But in the end of the day, what you find is that you basically have your fermionic action where you simply project to the lowest Landau level. Then at the higher Landau level, they renormalize the R2, the mass per field phi, and then the rest just suppressed in the large n. So it sort of justifies the projecting to the lowest Landau level. And then now in this theory, where you only have lowest Landau level fermions and phi, if you integrate out phi, you get effective description on the lowest Landau level, which gives, again, Inches Hamiltonian. Okay, there's some small remark which I can skip, that, or maybe I say that actually you should also do, to really get that Hamiltonian, you should also do the static approximation, because here this number squared actually includes also time derivative. But to really get that answer, you should work in the static approximation. But universality is forgiving. A lot of things you can do approximately, and then at the end of the day, you flow to the fixed point that you're after. Now, about this density channel that was mentioned before, it turns out that, well, okay, in the Ising case, tuning the density channel to a particular value removes this basically to alpha equals 1, removes this intra-lay interactions, and it was analyzed by using the Holman perturbation theory before, and it basically corresponds to switching off some irrelevant deformations, which improves the numerics. At the same time, though, because we have this effective field theory written just in terms of the real scale of phi, you could ask, well, okay, this theory has one critical point, fixed point is just the Ising CFT, but it also has Gaussian critical point. Can we tune it to the Gaussian critical point? Unfortunately, if I just use the minimal Ising mounted theory, where it's with just phi and tube size, you can check that the interaction, the phi to the 4th interaction that you get induced by quantum effects, it's positive, and it can only be tuned to 0 in some sort of singular limit of couplings. So it's not really accessible. However, if you add this density channel, which corresponds to including additional Hubbard-Satonovich field rho, which then like you do not tune this field to critical point, so this field remains non-critical, then you get additional sort of handle on your effective field theory, and you can tune U4 to 0, and then you must keep U6 positive, and then this allows you to flow. This is the so-called tricritical route, which in 3D, you know that it's known that it flows to the Gaussian point, and indeed, this gives you the fuzzy sphere, one of the fuzzy sphere realizations of the free scalar, which is due to these people, where they precisely tune both the interlayer and intralayer interactions, these type of interactions, such that the Hamiltonian, instead of Ising fixed points, gives you the free scalar. Now, in case you haven't noticed, all these things I told you so far already answered all the puzzles I mentioned earlier. Such as we have this sort of way of thinking of this construction as a controlled projection, the symmetries match, and Lorentz invariance can be explained using standard effective field theory sort of techniques. Furthermore, this because now you have this approach, you're less reliant on universality, and you can imagine generalizing to other possible theories, even to gap theory. Now, in the rest of the talk, I'll give you just a few more examples and ideas. First, now it's like really easy, trivial to generalize it to also include the Young case, because all I have to do is start with this mother theory and add imaginary deformation of this form, which, from the point of view of phi EFT, will allows you to tune to the Young point. On the other hand, you can integrate out phi, and it introduces this sort of deformation, which was previously considered in these two papers where they studied the non-unitary CFT. Another generalization is, I just want to explore a few generalizations that are sort of on the surface. I can consider complex HS field instead of the real one. In this case, I can have U1 symmetry. So I couple again two Dirac fermions to complex field phi in this way. So there is a symmetry where I rotate phi and size. Then if I integrate out psi, I get the usual effective field theory, which can be either tuned to O2, a critical point, or it can be in the spontaneous symmetry breaking phase, where you might get boson. On the other hand, if I integrate out size, I get this, phi, I get this sort of Hamiltonian, which called easy plane, because you can the magnetization can rotate in the XY plane without any energy cost. So in this theory, I can. So if I look at specifically at the symmetry broken phase, where absolute value of phi has a vev, then I can compare it with the Yin-Chan's another Yin-Chan's model, which is this free scalar model. And in fact, these two were also included a spinning term that gives you sort of conformal mass on the curved background. So these two models, if you analyze them numerically, they're basically indistinguishable. Like they differ like in some fourth digit or so, but they are not algebraically equivalent. So it means that they really differ by highly irrelevant operator. But they both have also this issue that there are some other contaminants in the spectrum which are related to the fact that the absolute value, the massive field that acquires mass, this spontaneous interbreaking, it's not really decoupled, because you can estimate the window for it to be decoupled from the spectrum, from the boson, and this window for finite n is quite small. So it contaminates the spectrum. What one could try to do is instead consider the compact boson and like look at the following model theory, where instead of complex phi, I have just a phase. And then, of course, here, if I integrate out fermions, there's no potential generated, and I get just a compact boson. Whereas if I integrate out psi literally in this, theta literally in this theory, it's an ultralocal variable, so I can generate some potential. Well, this one has not been analyzed numerically yet, so it's like the status of proposal, but it would be interesting to see. Now, there's some other examples which I will skip. Well, there was some example of model theory for the OM model, which is also easy to write. But I also wanted to emphasize, so far, it appears that all the existing fuzzy sphere Hamiltonians, for all of them, you can write this sort of local model theory, which is, so I haven't found any counterexample so far. The comprehensive review of all possible model theories of cooperation. And the final remark that I wanted to make in the remaining minute or two, that when we integrate out the field phi, we deal with expressions like this. So there's a quadratic kernel of phi, and then it couples to O, which is like a fermionic bilinear. Then actually, the field that is supposed to flow to the CFT point is phi, because that's the field that enters the local EFT that we tune to the CFT point. But in general, it differs from these correlators of fermionic bilinears by some Gaussian noise ingressing with K. So that's a subtlety that can be dropped when K is ultralocal. Like in the examples we looked at so far, K was like a delta function plus derivative of delta function. So it leads to quantum terms and it can be dropped. But in more general examples which we can imagine, these Gaussian noise should be included, and that there's a toy example. So especially if we want to generalize this to gap theories, which there's hope that eventually, I believe it should also apply to gap theories. And there's the toy example for that is if I take again a pair of a pair of Dirac fermions of masses plus minus m and couple them to non-compact photon, well, non-compact in order not to deal with monopole sectors. Then, and I run this procedure, then of course the corresponding Gaussian kernel is not ultralocal. But and then the model that I get if I ignore the Gaussian noise that I included before, it's just going to be a very simple model of electrostatic interaction on the lowest lambda level. And this precisely misses the photon because photon lives, so you sort of draw a baby with the water, because a photon lives in this Gaussian noise that I throw away. So it is important to keep in such theories which are not conformal, where I have to look at the interaction, the kernel for phi that is not Gaussian. It is important to keep that Gaussian noise. And that was it. So there's some outlook for things that have to be done and conclusions, which I'll just leave. Thank you.
Any questions?
Thank you for the talk. I have two questions. First, as clarification, when you have this model theory and you go to the two different theories, are you claiming that the two theories that you go to are exactly the same, or is it just that they can be continuously connected with a parameter?
So the most ambitious claim is that they're exactly the same, but in these cases that I explained that I had to do some approximations along the way, so they are really it's more like they're continuously connected through parameters, or that they are in the same universality class. So in the most basic example of the Ising model, the most accurate statement is that they're in the same universality class.
It's still not clear to me why phase transition is very the parameters.
So I actually did not vary parameters. So what I did, I just integrate out, either I integrate out massive matter and use that to argue that there is a critical point, or I integrate out the light mediator and also then integrate out the higher Landau levels and obtain some non-local theory on the lowest Landau level in terms of fermions.
The second question is, what are you going to compute in the gapped phases? I thought the whole point is that you use the conformal invariance at long distance.
Right. So in the gap phases, and the tour example was this, the non-compact Maxwell. First of all, it's most likely going to be useful to replace fuzzy sphere by fuzzy torus, so that we don't have to deal with curvature. And then, for example, study the spectrum of this theory on fuzzy torus and try to identify some features, universal features at large n. Like, I don't know what features yet because that has not been done yet.
Quick question.
Thanks for a nice talk. In practical terms, so there is this issue that with the Lagrange, with the Hamiltonian that Yin Chen had, it was difficult, it was possible to tune the leading irrelevant operator to zero, but it was, people tried to introduce other parameters and tune further irrelevant couplings. And somehow it was difficult to do this from his initial formulation. With your new understanding of smother theory, can you perhaps tune more couplings? Do you understand why previous attempts didn't manage to tune more couplings?
So I did not specifically think about those previous attempts, but from this general perspective, like you saw, introducing additional field rho allowed was equivalent to this density channel, and it allowed to tune away some. So I would imagine that if you introduce more fields, you could possibly get more handles on your EFT on Wilsonian coefficients and try to tune them away. I haven't tried doing that, but I don't see any conceptual issues.
Okay. Perhaps it should be added to the list of puzzles that you can explain. Explain why previous attempts failed and now you can solve.
Okay.
Thank you.
So I have a question about generalization of this approach to higher dimension. So, for example, replacing this perspective on the fermions coming from lowest Landau level using super BT. Does that mean that your mother theory approach can actually generalize as far as to higher dimension?
Yes. Yes. So you can always imagine doing that in odd number of space-time dimensions, because spatial bias is even dimensional, and you can quantize that. So for sure. The really difficult question is how to do that in even number of dimensions. Because if you just literally do that, let's say in 4D, you can, analogous procedure will reduce you not to quantum mechanics, but to a 1 + 1 dimensional theory, which perhaps is useful. Another possibility is to actually consider 5-dimensional theory and think of a 4-dimensional theory as a limit of 5-dimensional theory, let's say, on a circle. And then, of course, in 5D, you can, again, do the quantization trick. So those are the two thoughts that I had before, but I haven't tried it.
So if there's no more question, let's thank Mikola again.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Hello, everyone. Welcome to the second Gong Show session of our Strings Conference. So, same as yesterday, we will have 12 short talks by 12 young, excellent researchers, 5 minutes each, ending with a gong sound. So, our first presenter is Elisabetta Armani from CERN, and please come to the stage.
Armanini. I'm a PhD student between CERN and the PFL, and I'm very happy to present these works that I did in collaboration with Fernando Aldai, Kellyan Herring, Sasha Ziboedov, and Andrei Belitsky. So the goal of these works was to bootstrap a stringy S matrix at finite Toft coupling. And with stringy, I mean that it contains higher spin massive particles. We found that a nice setup to do it is to consider scattering on the Coulomb branch of n equal 4 superior Mills in the planar limit. So let me consider n equal 4 superior Mills with gauge group, for example, un plus 4. And let me spontaneously break it in un times u1 to the 4th by giving a vacuum expectation value to one of the scalars of n equal 4 superior Mills. So as usual, when you have spontaneous symmetry breaking, there are new massive degrees of freedom appearing in the theory. So you have some heavy W bosons of mass mi and some light fields of mass mi minus mj. On the dual side, this Higgs of the theory can be seen by basically separating 4 D3 branes from the stack in the radial position of ADS. Now we consider scattering in this setup, and in particular we consider a the theory can be seen by basically separating 4 D3 branes from the stack in the radial position of ADS. Now we consider scattering in this setup, and in particular we consider a 4-point